Our team was tasked with creating an IoT embedded system which interacts with the monitor to display information to the user. We decided a great way to implement this project concept would be to design a home security system. The proposed security system would monitor a physical space for any disturbances. It would send an alarm to the homeowner's phone in the event that an intrusion is detected. Furthermore, the system would have a disarm function where the user could disarm the system to prevent an alarm from being raised when they return home. This design of the system requires the use of many concepts we have previously learned in our labs, including circuit design, software research and specification, and interrupt-driven software development. The hardware and software components of the alarm system include a Raspberry Pi Model 2B running the Raspberry Jessie Lite operating system, an 8GB micro SD card, a HC-SR04 ultrasonic sensor, a Logitech webcam, a Wi-Fi adapter, a red LED, a mechanical button switch, various resistors, prototyping board, connecting wires, and this is all programmed using Python 2.7. The Raspberry Pi 2 Model B has many general-purpose input-output pins that we can use to create our alarm system. This figure illustrates a map of these pins and their corresponding GPIO pin numbers. We can see that there are a couple of 5V and 3.3V leads, multiple connections to ground, and plenty of GPIO pins that we can use for the logic and control of our system. Each GPIO can be set to either receive an input signal or send an output signal, depending on our needs. We chose the ultrasonic sensor to detect an intrusion within our system. This device allows one to calculate the distance of an object in front of it, which bounces ultrasonic pulses to and from the sensor. Through continuous polling, our microcontroller will be able to detect a change in distance when an intruder crosses its line of sight. We can see the 4 pins on this sensor: VCC, trig, echo, and ground. This device requires 5V to VCC, and we can connect ground to a grounded pin on our Raspberry Pi GPIO. The trig pin will trigger an ultrasonic pulse from one of the ultrasound modules on the device, and therefore will require an input signal from our microcontroller. The echo will listen for a rebounded ultrasonic pulse, and will output a signal to our microcontroller when such a signal has been received. There is one thing we need to worry about with respect to the output signal of the sensor. It returns a signal of 5V, however we would like to limit the voltage of our GPIO pins to receive 3.3V in order to protect them from any sort of damage. This can be accomplished through the use of a voltage divider using 1 and 2 kilo ohm resistors in the arrangement shown in the figure below. The Logitech webcam is perhaps the easiest device to connect to our microcontroller. We can simply use one of the USB 2.0 docks to interface with the camera, and driver software is already found on the operating system. The connections involving the disarm button and alarm LED are very simple and straightforward. The button will be connected from a 3.3V pin to a GPIO input pin. The LED connection begins at a GPIO output pin connected to the LED and a resistor in series, and then back to the ground. In order to get our security system up and running, we need programming tools that produce software able to do several different operations. We need to manage the GPIO pins in such a way that the microcontroller correctly identifies input signals versus output signals. We also need to create routines that can monitor the state of the sensor, keep track of time, take photos and send emails with attachments, wait for button presses to trigger interrupts, and create threads that can blink an LED during an intrusion. We found that Python 2.7 handles all of these problems quite well with its varied libraries. The program runs in a loop checking the distance from the sensor in regular 1-second intervals. If the program reads a distance that is below a certain threshold, the program takes a timestamp at that moment and takes a picture of the scene. The program then enters a disarm mode, where the program waits 10 seconds for an interrupt in the form of a button press, while a separate process thread blinks the LED concurrently. If this wait interrupt times out, the program will send an email to the homeowner alerting them of the security breach, including the timestamp and the photo taken by the camera 10 seconds prior. If the alarm system is disarmed via button press, the program resumes monitoring for another intrusion. This program terminates with the keyboard interrupt where all GPIO are reset to low and the processes end.